photovoltaic cell. The terminal voltage V and the terminal current I that is supposed to flow out of the terminal A here is indicated. And we also know, we have seen before, the equivalent circuit model of this photovoltaic cell, and that is like this. So you have this constant current source representing the photocurrent. The photocurrent IP is basically directly proportional to the incident solar power. This is primarily the source. Rest all other parameters are sinks, dissipators. And we shall now try to study this equivalent circuit model a bit further and try to arrive at the equation for the terminal current with respect to the various parameters of the photovoltaic cell. So using this model, we shall further get some more insight into the photovoltaic cell, which will be useful for selection, choice of the photovoltaic cell. Let us clear some place and position the equivalent circuit here. Looking at the equivalent circuit, the current IP is equal to ID, the diode current, plus the current through the resistance R shunt, plus the terminal current I. If you consider this as the reference node, the voltage at this node again can be seen that it is equivalent to V plus this drop, and this drop is having a potential which is positive here and negative here, and therefore you have at this point V plus IRS. Therefore, current flowing through R shunt is V plus IRS divided by R shunt. Rearranging, we get the current, terminal current, which is IP minus the diode current ID minus the current flowing through R shunt, which I can write as V plus I into RS by R shunt. Now the diode current, we know from the PN junction theory, it can be written as I naught, which is the reverse saturation current, e to the power of voltage across the diode, which is nothing but V plus IRS by an ideality factor N into Vt minus 1. So this is the current equation for the diode. It comes from the PN junction theory, which you will find it in any electronics PN junction chapter. Typical reference would be the integrated circuits electronics by Millman and Alkayas. Now what is Vt, N and I naught? I naught is the reverse saturation current. Vt is the volt equivalent of temperature. Vt is the volt equivalent of temperature and given by Boltzmann constant into the temperature divided by Q. Q is the electronic charge in coulombs, K is the Boltzmann constant, T is the temperature in degree Kelvin, and if you substitute the Boltzmann constant in the electronic charge, you will get this to be a value T by 11,600. N is a parameter which is dependent upon the material, and it has a value equal to 2 for silicon. And it has values which are different for other semiconductor materials. Now, I naught itself, called the reverse saturation current, is also dependent on the material and the doping of the p and the n junctions. Not only that, I naught is dependent on temperature. So this is given by the following relation: K T to the power of m e to the power of minus v g by nVT, the same nVT coming into the picture here, where K is a constant which depends upon the dimensions of the p-n junction and also the material properties. And VGO is numerically the equivalent band gap energy in electron volts. So VGO is basically the forbidden band gap energy, which is EGO in electron volts. So this is again a numerical value which will come in there. VT of course is known, which is same as written above, T by 11,600. N again is 2 for silicon. T is the temperature in degree Kelvin. Some typical values are like this. You have M, which is equal to 1.5 for silicon. And VGO varying from 1.16 to 1.21, again depends upon the grade of purification, whether it is electronic grade, solar grade. The solar grade for PV cells will be more closer to 1.16 volts. So these are the typical values using which you can get the reverse saturation current for a particular p-n junction device. The entire model of the photovoltaic terminal current can now be written as IP is the photo current directly proportional to the incident solar radiation minus I naught e to the power of V terminal voltage plus IRS by nVT minus the current flowing through the shunt resistance, which is given like this. So this would form the terminal current model of the PV cell, and this can be obtained easily from the equivalent circuit as shown above. So this equation of the current, the word of caution at this point, you see that the terminal current I is a function of itself, I appearing here in the equation. So this means that this is an acausal equation, which means that the present state of I is dependent on the present state of I itself. Algebraic equation, and you can land up. However, in practice, you should understand that the diode is not an ideal diode. It has junction capacitances, and the junction capacitance across the diode will take care of the causality problems, which means the voltage here will be a state, and it will have history and memory. And therefore, the current here will not cause a problem if you simulate this particular circuit in SPICE, because SPICE takes the real model of the diode along with the junction and diffusion capacitances. Whereas if you try to simulate this equation in Simulink in MATLAB as an equation, it will give you algebraic loop problems. So for that, what can be done is to use a memory block, a history block, pass this current I through a history block and use that to calculate the terminal voltages here. This would give some memory effect and can make the simulation work without problems. However, for our analysis and selection of devices and to understand the PV cell, this model is more than sufficient, and we will use this model to understand the PV cell further and characterize it.